In 6.6, we're going to wrap up our work with linear systems by working with systems of linear inequalities. So our learning objectives for this section are to solve systems of linear inequalities. And you've already worked with linear equations, systems of linear equations. You've already worked with linear inequalities. And this is basically taking the same ideas that evolved from linear equations to systems of linear equations, relating it to linear inequalities and systems of linear inequalities. So the vocabulary you're going to need is, what is a system of linear inequalities? What is the solution of a system of linear inequalities? And what would the graph of a system of inequalities be? So when you think of what this is all about, a system of linear inequalities is two or more linear inequalities, in the same way that a system of linear equations was two or more linear equations. And it would look something like this, two or more. And often I think you'll find you're going to see the or more part in inequalities more frequently than you would see them in systems of linear equations. So the solution of a system of linear inequalities is an ordered pair that is a solution to each inequality of the system, in the same way that a solution of system of linear equations would be. This is the same. So again, we can test the ordered pair, and we're looking for a true statement. Okay, if we get a true statement out of each equation when we test the ordered pair, then we know that it's a solution. And then the graph of a system of linear inequalities is a graph of all the solutions of the system. And in this case, when you're thinking about linear inequalities, we would graph and then we would shade an area of the graph. Typically, in a linear inequality, when we graph it, the line creates a boundary line and we shade one half of the graph. In this case, the area where the shaded areas overlap, that's the graph of the solutions of the system. So we're looking to find these and graph these solutions. We want to graph each inequality and then identify the intersection point of the half planes, and that's what I'm talking about, of the intersection area of the shaded areas. Okay, so let's look at how that plays out when we graph. I know that I've got this equation where I've got a y-intercept of 1 and a slope of 2, so I'm going to go up 2 and right 1. I could go down 2 and left 1, same line. And then my line is going to be solid because this says or equal to, so I'm choosing the solid line. And I go down 2 over 1, down 2 over 1, down 2 over 1. I'm going to be somewhere around here, right? I'm off a little bit, so I'm deliberately putting it off. And then I'm going to move my line to where it belongs. So a little bit off, so let's rotate this around a little. There, I'm pretty happy with that. And then I want to shade the correct half of the graph. Well, this is y is greater than, that's above the line. So this is the area that is the solution of that one inequality. When we look at the other inequality, I have a y-intercept of 4. So let's see, 1, 2, 3, 4. And I have a slope of -1. So down 1, left 1, up 1, right 1. This is going to be a dotted line because it says less than. So I'm going to pull out my dotted line. And then I want y values that are less than this line. So less than the line would be here. And you see that the area that overlaps is this area here. Right? This is the solution of my system of inequalities, the area where the shades from the two different lines overlap. Let's do another problem like that. Now we've got a third equation. So I have x plus y is less than 10. So if I put that in slope-intercept form, y is less than or equal to -x plus 10. So I've got a y-intercept of 10 and a slope of -1, and I'm going to have a solid line. So let's go ahead and graph that solid line. So about there, looks good. And I know I'm just going to indicate which side I would graph. I would be less than, so I'd be graphing on this side. And I'm not going to shade until I know the exact area that is the solution. Now here I have this equation I want to put into slope-intercept form, so I'm going to add y and subtract 2. So I'll have x minus 2 is greater than or equal to y. Or I could read this as y is less than or equal to x minus 2. So I have a y-intercept of negative 2. That was terrible. Let me try to be a little more accurate with that. Negative 2. And a slope of 1. So up 1, right 1. And then I have, again, a solid line because it's or equal to. Wow, I missed again. Get that line in the right spot, about there. Okay, and then this one I'm graphing for y is less than. So you notice that's over here. So now this area up here that's above this line, that's not part of my solution. And then we want y is greater than or equal to 2. So y related to 2, that's going to be a horizontal line. This is, again, a solid line because it's or equal to, and it's going right through there. And I want y values that are greater than this line, that's above. So my solution is this little triangular area right here. And that's my solution. Okay, so let's take a look at another example. So just as I have taken equations and created the graphs, I can take the graph and create the system. So we had a system of linear inequalities in the last problem, and we graphed them. And in this problem, we're going to take the graph and we're going to write the equations. As we look at this graph and we try to write the inequalities that will make this system of inequalities, you can see I've got a line here. I'm going to call that line number 1. And down here I have this horizontal line I'm going to call line number 2. And then this other line is line number 3. And we can see that the solution area is above this line, it's above that line, and it's below this line. So we want to make sure that we write these out. I'm going to start with number 2 because it's the easiest. So I know that that's going to be y is greater than, it's dotted, so I know it's not or equal to. And this boundary point is 1, 2, 3, 4, 5, 6, negative 6. So y is greater than negative 6. If I look at the next, I'm going to work on line number 3 here. It's a solid line. I know we're below it, so that means that it's going to be less than or equal to. And I can find the y-intercept is right here. It's 1, 2, 3. It's negative 3. And if I look at the slope, it's up 1, right 1. That's a slope of 1. So this is going to be x minus 3. And in my final line, line number 1, it's a dotted line, and we're above that line. So again, it's y is greater than. My y-intercept is negative 1, and my slope is down to right 1, so it's negative 2x. So our system is y is greater than negative 2x minus 1, y is greater than negative 6, and y is less than or equal to x minus 3. Looking at this information in context, we've got this situation where we're going on a hiking trip and we want to make we want to make a mix with x ounces of peanuts and y ounces of chocolate pieces. And then we want the mix to have less than, that's an important word, right? Less than 70 grams of fat and weigh less than 8 ounces. An ounce of peanuts has a certain number of grams of fat. An ounce of chocolate pieces has a certain amount of grams of fat. And I want to write a system that models the situation. So I'm going to start with some simple ideas. I know that we want to have less than 8 ounces. So if I have X ounces of peanuts plus Y ounces of chocolate pieces, I want it to be less than 8 ounces. Okay? Now when we look at fat, I see 14 grams of fat in the peanuts. So the grams of fat in the peanuts would be 14 times X. And then chocolate, it would be 7Y. And we want that to be less than 70 grams of fat. And I would also probably add in that X has to be greater than or equal to 0 and Y has to be greater than or equal to 0, because I can't use negative values, right? I could reduce the amount of fat by doing negative peanuts and more chocolate, but that's not practical. That can't be done. Okay, so popping through and picking through the specific information, we can write out a system of inequalities that models this situation.